morning. I'm Itumizo and hello our lovely Abbas Function to my beautiful and gorgeous and good looking friends. So it is a lovely morning. It's this Friday, lovely Friday morning of November. My groupmates, which consists of Tina, May and I, are going to talk about our combined functions of relative-based situation for our Abbas Function ISU presentation. So we're going to be talking about the combination of trigonometric functions and exponential functions in sound wave, which is quite similar to what Shahid and Yanwun has presented. So here, as a first speaker, allow me to do a little recap. So a sound wave is actually a longitudinal wave in which particles is moving back and forth horizontally instead of moving vertically like the water wave. And so you can see here the particles is forming a compression in which the particles crowded together to form a crust, and this part is where the particles are spreading apart, which is from the throat in the refraction part. So, sound wave can be characterized by three categories, which is the wavelength, amplitude, and frequency, which will be explained by my lovely friend Tina.
Okay, the wavelength is actually the distance from the crest of the wave to the other one. The frequency is the number of waves that pass the point to each second, while the amplitude is the measure of amount of energy in a sound wave.
Okay, so this is the wavelength, the distance between crest and crest. This is the amplitude, the distance between the top of the crest with the normal point, and the frequency is the number of complete oscillation present in 1 second. Okay, so loudness and pitch. Loudness refers to the amplitude in which the higher the amplitude, the louder the sound. And pitch refers to the frequency, the higher the number of frequency present in 1 second. Yeah, and the higher the pitch. So, our first function is trigonometric function, in which it will be this function. You can see that? Yeah, I know it's complicated. So our choice of function is fx equals to 156 in x, in which it derived from the sound of a key of a keyboard. As B is a D flat. So we take a frequency as a y-axis and time as an x-axis. This is E flat. Yeah, listen. And next, I'm going to talk about the key features of the function, in which the domain which x includes all real numbers. I know that we cannot put t as negative because it's time, but this graph is only to show you that it is a continuous graph. So the range include all real numbers, but it's between negative 156 and 156, which as you can see in the graph, the bottom here is 156, it's not 160. Can't see it today. So this is negative 156 and this is 156. Okay, so maximum value refers to the highest frequency and minimum value refers to the lowest frequency. The amplitude, in which the maximum value minus the minimum value and divided by 2. Okay. So let me explain to you why is it even if we press the key notes like continuously, why is it forming a gap? So actually, human ears is only audible between 20 Hz and 20,000 Hz. So actually, well, you can see here, in our case, we're using like 156 Hz. So it's our ear is only audible from here to here. So we have a gap here in which the refraction is occurring. So that's why we cannot like hear the notes like continuously unless we use a sustainer, which is not in our case. Next, exponential function explained by T.
Okay, the exponential function that we use is fx equals to 16 power x minus 5, because this part of the graph is actually the part where we don't push the key notes on the piano, while this part is actually when we push two key notes at the same time. The increase of this frequency, this frequency increased drastically because we choose two different key notes and two different frequency notes together. The notes that we use for this graph is D flat and also C minor, which have two different frequency. Where D flat is actually a low frequency, while C minor is a high frequency note. And the key features are X is lower than 5. The range is Y more than 0, and the graph actually has a vertical asymptote of X equals to 5. It doesn't have any X intercept, while the Y intercept is actually at 1.
Vertical asymptote?
And Miss can explain the combination function.
Can I look at the graph again? The exponential? Where's the vertical? I thought exponential graphs don't have vertical asymptote. Is that right? I do exponential graphs horizontal, isn't it? Yeah. So gotta change that. Okay.
Okay. This is a graph of our combined function. Actually, when you enter the true graph, you see that the first part of the graph is when you play the D flat key. You can see that the frequency goes up gradually to the maximum and then go down. As you can hear the sound getting louder at some point and then eventually fades. So when the first sound nearly fades to at least to our ear, we play the both D flat and C minor key at the same time. So that you can see that the frequency goes automatically presenting as D equals. In reality, the frequency won't go at infinity forever. It will go down again to 0 point at the same time, but you can't see that on our graph. And actually, you can see that most part of our graph is on the negative scale, and like my friend Zaidi has mentioned, the time cannot be negative value. But we wanted to present only how the frequency goes up and down, the way the frequency changes when you're playing with the keyboard key, especially with a song with the different frequencies. Key features. Make some mistake. Actually, it should be negative 156. And actually, our graph don't have the intervals because actually there is on this side, this significant pattern of the graph going on, and from this side it goes up to infinity. But we wanted to present only this interval, so we put restriction on domain and range. There is no asymptotes, and we didn't include other key features like X and Y intercept because it is difficult to mention. So, real life application. Called creation of music. Actually, there are many other applications for frequencies like modulated frequency for the radio transmission or used in telecommunication. But since our example is keyboard, we just take it to the creation of music. You can create awesome piece of music by combining the sound wave, especially with with different frequencies, and you can use any so-called musical instruments or anything that comes up on your mind, especially as long as it produces the audible sound. Let us show you a video.
No.
Thank you.
Sorry. Oh.
Okay.
It is a glass harp. The glass of different sizes produces different frequency with sound wave, and when you combine it, music is created. And thank you for your attention.